Which printer makes better 3D prints? The Bambu Lab H2D with its dual quick swappable hot ends and its ceramic style heater, or the Bambu H2C with the left quick swappable hot end and the right being the new automated tool changing induction style hot end. They're similar enough but different enough to make me wonder if one of these printers will produce better results than the other one. So today we are pitting the H2D against the H2C and running tests in as many materials as I can. We're also going to be running torture tests, and finally we are cutting each hot end open to see what's on the inside, all to find out which printer really reigns supreme. So let's get into it. Now that I've seen it in action, I'm pretty confident that the induction style heaters on 3D printers are going to become the new standard, especially with there being so much demand for multicolor printers, making fast heating an absolute necessity. But there is one question that comes to mind: do we need to trade something off for that fast heating, or is it literally better in every way that matters? The H2D and the H2C both have hot ends which use the more common ceramic style heater. It is a thin heater mounted to the back of the hot end heating assembly. The heater heats up, the heat moves through the hot end mount, which I believe is plated copper, and then into the hot end itself. The plating isn't just there for protection, it reduces heat loss thanks to that highly reflective surface. There is a thermistor mounted down behind the hot end so the printer has an accurate value for the temperature, and it's a pretty straightforward setup that's already proven, but it is not really that fast of heating, at least not compared to the induction hot end. Induction heating is common in industry, and one of the coolest applications I've ever seen it used in is to quickly heat up cast iron or steel in an incredibly localized area, and then that area is quickly quenched, resulting in a hardening only where it needs to be. In that example though, the temperatures change from basically room temp to 1000 or more degrees Celsius in just a matter of seconds. In the case of a 3D printer, we're only asking for a few hundred degrees Celsius, so the 3D printer application is much less demanding. Because it heats up so quickly and so precisely, temperature monitoring and control is much more critical, but from what I've seen so far, it has worked flawlessly on the H2C, so it may just be the ideal solution for 3D printing. With the ceramic style heater, we have a much more traditional type setup because it's bulky, uses a big silicone sock as an insulator around the hot end. We could also see while using the thermal camera that the sock does get really hot. But like most socks, the purpose is to reduce heat loss from the cool air blowing on it and around it, and it's also to prevent filament from sticking to the hot end. The induction heater is not really anything like that. It's all exposed. Kind of a bare bones setup. There is a thin layer of insulation wrapped around the shaft of the induction hot end, and then down near the bottom there is a silicone sock, but it's a very minimalist style, which is there for the same reasons as the traditional sock, but this one fits very tight and it snaps in place, and it also does not seem to suffer from any wear and tear like the other style does. Unlike ceramic heaters, the induction setup heats up the hot end directly, so it will be very responsive to changes in temperature. Now, I believe that the hot end is also so exposed not just because that's what's needed for the tool changing setup, but also because it does promote faster cooling, so when it is not needed, there's not as much oozing. Overall, at least on paper, the induction heating does seem like it's superior. Bambu isn't the only one moving to induction either. Bondtech's new Index system will be using the induction heating setup also, but others like the Snapmaker U1 uses ceramic, likely because of their tool changer setup and it can preheat while it is docked. And the Prusa XL uses a cartridge heater for the same reason. Before I run anything, I'd like to make this test as fair as possible, so I'm going to recalibrate each printer, and that includes using the Vision encoder on both. And to go the extra mile, I've also cleaned them both really well, and I've also re-oiled and re-greased all the rods and the screws on both printers too. From my testing, cleaning really doesn't affect print quality over the short term, but it will overall make the printer last a lot longer, and that's even more important on the H2D with the laser because it does get dirty quicker and it does require a little bit more cleaning. So both printers are now fully clean and recalibrated and ready to go. I want to make this testing as completed as I can, so I'm going to be printing with all of these different materials. So I have PLA Basic, I have PLA Silk, which is also a dual color, really cool one. I have PETG Basic, PETG High Flow, PETG Carbon Fiber, and PETG Translucent. ABS, I have ASA, And then I have some softer ones, TPU 95A, and then I have this one here, TPU 90A, which is quite flexible. So that should make for some pretty complete testing on these two printers. These are all pre-dried and ready to go, but I won't be splitting these spools. I'll just be switching them back from one printer to the other. I will allow the printer to auto-calibrate each filament because that is what these printers are designed to do. And I am very happy that it does that. So dynamic flow calibration accuracy is completely up to the H2D and the H2C. I've run each benchy with each material on both printers, and now I want to do an overhang torture test on each printer. We will be using PLA for this one to see if cooling on the overhangs are impacted at all. I'm also going to be running Autodesk FDM test print on PLA to see how each printer performs with a combined torture test. And I'm going to also run my bridge burst torture test, which is designed to test bridges of all distances in all directions as well. Even though these printers have effectively the same ratings for volumetric flow, I'm going to use a 0.4 millimeter nozzle hot end on both and see how much volumetric flow we can reach before we start to have problems. Now the tests usually reference ABS at 280 degrees Celsius, so we're going to start with that for our test, and I'm going to be using a 28 millimeters cubed per second going up to 70 millimeters cubed per second, and we'll see how far each printer can reach before we start to have problems. I do want to keep in mind these are not the high flow hot ends installed because I don't have a high flow hot end for the H2C yet to compare against. They are just the standard flow. So this side is all the parts printed on the H2C with our induction style hot end. So that is only looking from the front, the right hand side. These are all the parts on the H2D printed with the quick swap hot end. Again, apples to apples as much as possible. So only the right hand side. So rather than me going through and comparing every little detail on every single print that I made, which could take half an hour or more, what I'm going to do instead is at the end of the video, I'm going to show you a very detailed video of each of these. You can take a look for yourself if you'd like to. But what I'm going to do instead is tell you the main differences that I'm seeing, if there's anything major that's come up in all of this testing. So here we have basic PLA, and then we have dual color PLA silk with that nice sheen to it. And I would say if you were to mix these all up, you probably wouldn't be able to tell which came from which printer. They're all so similar. On the PLA silk, I did find the H2C is slightly better when it came to these very, very minor imperfections, but we're talking so slight, it's probably not even worth mentioning here. It's just that with the shine, you can really see it in the light there. So the H2C, slightly better for the silk prints, but again, very minor. And here we have all of the PETG prints, PETG carbon fiber, PETG high flow, and then this is the older style basic PETG, so the one that was prone to getting stuck onto the nozzle, stringing, and so on. All these prints really, it's the same with the PLA. You can't really tell the difference from one side to the other. There are some areas where the H2D might be slightly better and some areas where the H2C might be slightly better, but they're so similar. I think if you were to mix them up, you couldn't really tell the difference. Both printers seem to do a really good job, and PETG carbon fiber does tend to be an issue when it comes to bridging, actually PETG in general, and they all seem to do decent when it came to bridging these prints as well. So these are also PETG. This is PETG translucent. I wanted to talk about this one separately because the prints both turned out really nice, but the bottom of this one tore off from the H2C. And the reason that it tore off is because I had applied at that point multiple layers of glue stick, and I was trying to remove it when the bed was still hot. And unfortunately, the bond to the bed was actually better than the bond to itself, and it just tore the bottom right off of it. But the rest of the print turned out really nice. Again, the same as the last ones. You cannot tell the difference between these. If you were to mix these two up, you wouldn't be able to tell unless you looked at the side. So here we have ASA, and these are black, so they're a little bit difficult to tell when it comes to imperfections. Really, the only difference I can see is bridging on the H2D is not quite as good with ASA as it is on the H2C. We have really nice bridges across here, and here where it transitions into the arch, it's better than on the H2D. The H2D just struggled a little bit right there, and up on the top there on that bridge. So I would say the H2C performs slightly better on ASA than the H2D. And here we have ABS, and we have basically the identical scenario to the last one. We have a little bit worse bridging and a little bit worse transition up here on the overhangs on the ABS, on the H2D versus the H2C. You can see the bridge there looks really nice, and then the overhang there as it transitions into the arch looks nice as well. So here we have TPU. This is 90A, so it's quite flexible, as you can see there. So there are some differences on the TPU. There's actually quite a few. They're not all good on one and worse on the other. They kind of flip back and forth. So the bridges are not quite as good on the H2D as the H2C, but I would say the overhangs seem to be slightly better. I mean, they're not that good. You can see there's a difference there. So slightly better here versus here. And there are these tiny little imperfections. It's going to be difficult to see. There's some very small imperfections in the surface on the H2D, and we don't have those tiny little voids on the H2C. So there's an improvement there as well. So overall, I would say the H2C performed slightly better on this soft TPU. And now we have 95A TPUs, so not quite as soft, more rigid than the last one that we saw. This is white, so it's going to be really difficult to see any imperfections in here, but basically we have the exact same scenario. We have these bridges here, which are saggy, and not so much on the H2C. And you can see the overhangs there. Again, similar to the last one, probably a little bit better for both. The overhangs here, a little bit better than the overhangs on the H2C. Overall though, these two are a little bit more similar than the last ones that we looked at, with the H2C probably coming in slightly better because of these bridges. And here we have our overhang testing, H2D, H2C. I will say the overall H2C looks much more uniform on all of these different sides than the H2D. The H2D did not do too bad, but there's some of the sides that don't look quite as good. So overall, the H2C did come in a little bit better than the H2D on the severe overhang testing. And for the bridge testing, very similar results. I found that, especially while I was watching it, the H2C didn't blow the bridges around quite as much as on the H2D. It seemed like the air was tending to move down a little bit more on the H2D than the H2C. So overall, this one did come in slightly better, but it is only just barely better. Again, we have a little bit more uniformity on this one. This one here, some of the areas are not quite as good, but again, they're not bad either. So quite good on both of them, slightly better on the H2C. Here we have the Autodesk FDM torture testing, and for the most part, these look so similar. Again, you could kind of mix them up not really be able to tell the difference. That is, until you flip it upside down. You can see there, look, we had some trouble with the bridging, a little bit of trouble on the underside, not so much. But if we look here on the H2C, you can see very nice bridging there, and the bottom as well. So overall, very similar results for both of these, except when it came to the bridging, where the H2C outperformed the H2D by quite a bit. And now we have max volumetric flow test. And if you're curious how I was able to get this test through Bambu Slicer, all you need to do to get that is switch to a printer, which is not a Bambu printer, and then switch back. And then up at the top, you will have a calibration menu that you can pick from, or you should anyways, if you're in the most up-to-date version. And then you can pick tests like this to run. So we have up to 70. That's 70 at the very top, so we didn't quite reach 70. In fact, it looks as though it was kind of telegraphing that it was going to have an issue here. So we were able to reach 57, 58 cubic millimeters per second on that test. So they were claiming we were able to get to 60, very close to the numbers that they had posted. And for the H2C on max volumetric flow, we have around 56 to 57 cubic millimeters per second. So not quite as good, but one difference that I noticed is that it was not telegraphing like the other one was. There were these almost vibrations that were coming through on the H2D. You can see there. And we don't have that on the H2C. There is just an immediate stop. It's kind of like a lithium-ion battery. When it stops working, it just stops. So right there, between 56 and 57. So it didn't quite match the H2D for max volumetric flow, but it is very close. It does look pretty awful though. If we take a magnet to the hotend from the H2D, this whole upper section is not magnetic. There's a hardened steel tip, of course, that's magnetic. So this is likely copper or an alloy of copper, making it an excellent conductor of heat. If we compare that to this hotend, we can't have aluminum, we can't have copper because they are very good conductors of electricity. They would not heat up very well. And that's because an induction setup works the best with a ferromagnetic material like iron or like steel, for example. So these coils that are wrapped around the sides, they induce a current into that material, and the resistance of this material itself to that flow of current helps to generate heat. Also, we have changing polarities at high frequency, so it's changing back and forth, and the magnetic polarity inside here is also changing, helping to generate even more heat. Steel in there, and a hardened steel tip as well. And that means when this hotend heats up from the outside in, it's going to take a little bit longer for it to heat completely uniformly compared to this hotend. And that might explain why we had max volumetric flow slightly better on the H2D than we did on the H2C. But why don't we open one of each of these up and see what's actually going on the inside. This is our quick swap hotend. I didn't do as good of a job of cutting this one open, but you can see what's going on the inside there. So we have a copper for the main body, a hard steel tip that's pressed in a few millimeters, and then it's just plated with probably nickel, and these work really well. Nothing too overly complicated about that. If we turn this over, you can see this does have a copper core, so that I did not expect. So it was attracting a magnet. So what actually is going on here is we have the outside layer of black, and maybe that's just to protect, or it could be for insulating. But then we do actually have an insulating layer, some type of material that's acting as a barrier. And I don't know what that is. That's why I wanted to wear a mask when I was cutting through it. And then we have a very thin layer of steel. So a steel sheath. And then beyond that, we do have a copper core. The copper is actually coated with this black material. And I'm not sure why that's there exactly, whether it's to help with the conduction of heat or maybe because the materials expand and contract at different rates. But in any case, there's a lot more going on this hot end than what I expected, but it is a pretty cool design. So the H2C performs slightly better overall in the more common tasks. The H2D performs slightly better in the high performance max volumetric flow rate. So I put the H2C slightly ahead of the H2D overall because quality is better than quantity, but it was a very tight race on both printers and they both did really well. If you found this video informative, feel free to drop a like and also help support this channel by subscribing if you're enjoying this type of content. I try and release a new and original video every single week. And also, if you're in the market for a 3D printer, I have a very short list of my top rated 3D printers down there below in the video description. And a quick shout out as well to all my Patreon supporters for helping to make content like this possible. Thanks for watching. I hope to see you on the next one. Which printer makes better 3D prints? The Bambu H2D with its dual quick swap hotend. What the?